Okay, moving on to question 2 of the Carbonyl tutorial. Okay, so in question 2, we have an aldehyde. Ethanol, to be exact, 2-carbon aldehyde, and becoming lactic acid at the end of it. So in stage 1, you can see that essentially, comparing the formula, a HCN is being added across the CO double bond. So if you compare the formula of this, CH3, CH, OH, and the CN. Alright, it's quite evident to you that the CN and H is added across the CO double bond. Okay, so therefore this is your addition type of reaction. And what are we adding? We are adding a nucleophile, a CN minus, and that's why this is called nucleophilic addition reaction. And therefore you're supposed to draw out the mechanism. Okay, so let's take a look at the mechanism. So first of all, draw out the compounds, the ethanol. CN minus is the nucleophile. So indicate the lone pairs on the C, negative charge, alright, because CN minus. Arrow must start from the lone pair on the carbon atom to the delta plus carbon atom. And this is the bond forming process. Okay, now because you are forming a carbon-carbon bond, alright, this carbon will now have 5 bonds, and as a result, you need to break a bond in order for this carbon, the carbonyl carbon, to continue to have 4 bonds. So, looking at all the bonds around it, this pi bond here is the weakest, and therefore it breaks. So, to show a bond breaking process, arrow should start from the bond and point to the oxygen atom. Okay, so this indicates a bond breaking process from bond to the O atom. Okay, the dipoles are essential. Why are dipoles essential? Because the dipoles, you need to show which is the electrophilic site. So in this case, the delta plus carbon is the electrophilic site because it attracts the nucleophile. Why is it delta plus? Because it's bonded to a electronegative O atom. Okay, this step is expected to be slow and you get your intermediate. Okay, so why is there a lone pair on the O? Because this pi bond that's broken, both of the electrons in this pi bond goes to the O, and that's how O gains an electron, develops a negative charge, and you have a lone pair on the O itself. Okay, so important for you to show the correct bonding. Take note, you are forming a carbon-carbon bond, so it should be the C connected to the carbon. Alright, so please don't draw your bond joining it to an N. Okay, so once this is done, this intermediate will have to be protonated in order to get the product. So where can you get the protons from? You can get its proton from a HCN molecule. So you can see, in this case, the lone pair, arrow starts from lone pair, point to the H. In this case, what am I forming? I'm forming a OH bond. Alright, so H, as we know, can only form one bond. As a result, this carbon-hydrogen bond, this CH bond, will have to be broken, with both electrons going to the C. So again, arrow starts from the bond to the C to indicate a bond breaking process. Okay, similarly, please show the correct bonding. Okay, so in this case, you get your product, your hydroxy stands for OH, hydroxy, and this is the CN group is called nitrile, so it is a hydroxynitrile compound, and you get your CN minus. Why is it CN minus? Again, this bond pair here both goes to the carbon, and that's how you have a lone pair on the carbon. The carbon gains an additional electron from the H and therefore becomes negatively charged. Okay, so this is your nucleophilic addition mechanism. Again, important for you to make sense of the mechanism, understand why arrows are drawn in a particular way so that you can better retain the information. Okay, so suggest why the carbon atom of the cyanide ion, not nitrogen atom, attacks the carbonyl molecule. So if you look at the cyanide ion, Cn-, and this was explained in lecture. So if we look at the dot and cross diagram of Cn-, so C has 4 valence electrons, N has 5, but because of the negative charge, we add 1 more to N, alright, because of negative charge, and therefore it has 6 electrons. Why do we add to N? Because N is more electronegative. Alright, so in order for it to both achieve octet, this is the dot and cross for Cn-, and you realize that Cn- have both a lone pair, both a lone pair on the carbon as well as a lone pair on the nitrogen. So both nitrogen and carbon are therefore capable of acting as the nucleophile because both have a lone pair. Alright, so you can see lone pair here, lone pair here. So the question is, why is the carbon atom that attacks the carbonyl carbon? So in order for it to function as a nucleophile, the atom must be able to use its lone pair to form a dative bond. Right? You can see the mechanism. You must use lone pair and sort of like form a dative bond. Okay, so comparing carbon and nitrogen, carbon is less electronegative than nitrogen, and therefore it doesn't like electrons as much. So the lone pair on the carbon can be donated more readily to form a dative bond with the carbonyl group. Okay, so this phrasing can be found in your lecture notes. Alright, so again, try to make sense of this. Okay, if not, I'm going to move on to B. Okay, in B, reaction 1 uses HCN with trace amount of NaCN under cold condition. We can also use trace amount of NaOH as we have learned from lecture. So NaOH, what does it do? Basically, you neutralize the H+, causing H+ to decrease, and this affects this particular equilibrium. As we know, HCN is a weak acid. It dissociates only partially to form H+ and Cn-. So if we decrease the amount of the concentration of H+, by Le Chatelet's principle, the equilibrium position will shift right to increase H+, which also leads to an increase in the Cn- concentration so that nucleophilic attack on the atenyl can occur. Okay, so again, reiterate, if you guys are talking about LCP, talking about equilibrium position, shift left or right, please include the equation with the reversible arrow. Okay, moving on, part 2 is possible to use HKCN in solid acidic condition. So just 2 reasons why this is preferred over using HCN. Okay, as we know, HCN is a toxic gas. Okay, KCN is a salt. So HCN is a toxic gas. It's harder to handle, alright, in the lab. So this 2 talks about safety. So it's the same reason. Okay, safety. Okay, so HCN is a toxic gas. It's much more difficult to handle as compared to KCN, which is a solid or can be aqueous, which is a lot easier to handle. And the main reason is because HCN, as we all know, it's a weak acid, right? Weak acid meaning that it only dissociates partially to give low concentration of Cn-. Compare this with KCN, which we all know that KCN it's a soluble salt, or because all salts of potassium are soluble, and therefore it completely dissociates and provides sufficient Cn- for nucleophilic addition. Okay, now in last part, reaction 2 converts cyanohydrin into lactic acid. You have Cn being converted to COOH. So this is your typical acidic hydrolysis reaction. You basically need an acid, aqueous acid, heat under reflux. So you can use either H2SO4 aqueous or HCl aqueous. But again, the state symbol is important because you need water in order for hydrolysis to occur. Okay, so heat under reflux because you need prolonged heating to get the product. Okay, moving on to part 2. So just in terms of the mechanism, alright, why lactic acid made in the lab does not rotate plane pairwise light. Okay, so if you look at the structure of lactic acid, this is lactic acid, CH3, CHOH, COOH. So if you look at lactic acid, we have CH3, CH, COOH, and then we have an OH group. So you can see there's a chiral carbon over here, but why is it that it does not rotate plane pairwise light? So if there's a chiral carbon and does not rotate plane pairwise light, this must mean that it must be a concept of racemic mixture. Okay, since there's a chiral carbon. So why is it that in the mechanism we result in a racemic mixture? Because in the mechanism in 1, we are looking at atenyl, right? So we have a delta plus, delta minus, and then we have our Cn minus, with a lone pair. And we know that around the carbonyl carbon, the sp2 carbon, is a trigonal plane. So your nucleophile can either attack from the top or the bottom of the plane with equal probability, generating equal amounts of each enantiomer, resulting in the formation of a racemic mixture. Okay, so there is an equal probability of the Cn- nucleophile attacking what? Attacking the sp2 hybridized, this particular carbon sp2 hybridized, right? And it's trigonal planar in shape, and it's electron deficient, carbonyl carbon atom. Alright, from the top and the bottom of the plane. Alright, when it attacks from the top, you get one particular enantiomer. If it attacks from the bottom, you get another enantiomer. So this leads to the formation of equal amounts of plus and minus enantiomer, resulting in the formation of a racemic mixture. So over here, this concept here is very similar to what we've discussed for SN1. Alright, where we have a carbocation intermediate and electrophilic addition. We also have a carbocation intermediate. Alright, but the thing you need to take note for nucleophilic addition, we no longer talk about carbocation intermediate. We are looking at the electron deficient carbonyl carbon atom. Okay, so the subject matter is changed because there is no carbocation in nucleophilic addition. Okay, with that, I'm done with question 2.